Okay guys, before us is a propped cantilever beam. Propped cantilever slab. It's a propped cantilever slab. So we are going to be analyzing this slab to get the quantity of reinforcement needed for the safe performance of this slab. The slab is a 4-meter span slab with a 10 kilonewton per meter load, uniformly distributed load, with one end fixed and the other end simply supported, making it a propped cantilever beam. So we are going to proceed with the moment calculation. In this case, we are going to be using, that is a moment M will be equal to FL squared divided by 10. We could have used FL squared divided by 8, but based on the previous slab calculated attached to this, using this would be uneconomical since there is already an adjacent and adjoining slab. So we are going to be using this for economic purpose. So we are going to proceed. M moment is equal to 10 kilonewton per meter times our length 4 squared divided by 10. Simplification of this gives our moment to be 16 kilonewton meters. Okay, so before we proceed, we should outline the parameters to be used for this for the purpose of this calculation. So we are going to be having our FCU to be 25. Okay, FCK to be 25 Newton per millimeter squared. FYK to be 410 Newton per square millimeter. And our D, we are using a slab depth of 150 mm minus your concrete cover of 20 mm, then minus an assumed 12 mm bar. So we are going to be taking half of that from the bottom of the slab to the center of our reinforcement, which is half of 12 mm, that is 6, and that leaves us with 124 mm depth. So let's proceed with the analysis. So first of all, we are going to calculate our K, which is M all over FCK BD squared. Our D is going to be 1000 mm, seeing that we are going to be working on the slab by meter, every 1 meter per meter. Okay, so K is equal to our moment, which was 16 times 10 raised to power 6, converting to kilonewton per meter, divided by our FCK 25 millimeter, multiplied by our B, which was 124 meter, then our D 1000. Okay, so we are making a mistake here. This is our D. This is our D, which is going to be squared, and our B, which is breadth, which is our B is 1000. So time multiplied by 1000. This is going to give us, and this will give us 0.0. Okay, that's going to be 0.042, which is just okay since k is not allowed to be greater than, which is less than or greater than 0.167, just okay. So the next step, we are going to be calculating our lever arm LA, which is equal to our lever arm LA 0.5 plus or minus the root 0.25 minus k all over 1.134 according to the new Euro code, and which must not be, which is either less than or equal to 0.95. Okay, substituting our values into this equation, we have lever arm should be equal to 0.5 plus the root 0.25 minus k. Our k was 0.042. 0.042 divided by 1.134. Simplification of this will give us, okay, after simplification we have 0.96, which is greater than 0.95. So we are going to proceed to use 0.95 instead to follow code, so we do not violate the Euro code rule. So the next step would be to proceed to the analysis to get the quantity and volume or the area of reinforcement needed for this particular slab per meter. So we are going to be using this formula AS equal to M all divided by 0.87 FYK lever arm and the depth. So we are going to be substituting all that we have calculated so far into this equation. That would give us AS is equal to, our moment was 16 times 10 raised to the power 6, that is converting it to millimeter to kilonewton, all divided by 0.87 multiplied by our FYK, which was 410, okay, 410 Newton per millimeter square, 410 Newton per millimeter square, and then our lever arm 0.95, then our depth, our D, which we calculated earlier to be 124. Okay, simplification of this would give us an area of reinforcement. After simplification, we have an area of reinforcement of 349 millimeter square. So after this, we have to go to the table of value to look for the quantity and the spacing for this particular area. So let's go there. Okay, this is the table we are going to be using to look for the quantity of the spacing and size of reinforcement to be used for this particular slab. So the area we calculated was 340, so we come to this table, we go to, from our assumption earlier we used 12 mm, so we are going to look for 349 millimeter square in the 12 mm row. That will lead us to the minimum. Okay, 377, a spacing of 300 mm is going to be okay for this particular slab, but for safety purposes we are going to reduce it to 275, and that would give us okay, so we can safely provide a spacing of 275 mm for this particular calculation. So we can say provide y12 mm at 250 millimeter center to center at the center, and from the table the row under which this comes about is 452 millimeter square. So that is our maximum area for this particular calculation. So let's proceed. The next step would be to calculate for distribution. We are going to be using AS is equal to 0.13 percentage BD. That's what we are going to be using for our distribution. That will give us 0.13 times 10 raised to the power minus 2, that is our percentage, times 1000, our B, then our D, 124. Simplification gives a result of 161.2 millimeter square. Hence, for this reason, you can simply say provide y10 mm at 300 millimeter. Thank you for watching. Please subscribe for more videos like this. See you in our next video.